these types of signals depending on whether or not they exist on the continuous time domain or the discrete time domain. Of course, the only difference between the two that we know so far is that discrete time signals use integer values on on the independent variable. So therefore, the period that we use to describe the periodicity of the signal is also going to be periodic, also an integer. Sorry. So then we showed that not all signals that have a repeating pattern over a region would necessarily be periodic. So an example of that would be this case. And then uh, once we're able to describe that as a periodic signal, then we sort of looked at what sines and cosines are, right? So we discussed what sines and cosines are based on what we know from, I guess, trigonometry and a little bit of phasors. So uh, in this case, we showed that period is just the reciprocal of frequency, and it's just the time it takes, really, that we perform one rotation over the unit circle. So whenever you're having any particular kind of confusion about sine and cosine, one thing that always helps me that I hope you can also learn to use would be the unit circle. If you go back to the unit circle, all of these properties from the sines and cosines always make sense, and it's all a little bit easier to imagine them if you look at the unit circle. So we also talked about exponential signals, how exponential signals are defined to be something like this. And of course, they also exist both in the continuous time and the discrete time. In the continuous time, we use E, which is the natural number, the natural logarithmic number, which is 2.17 something. It's a transcendental number, and it just keeps on continuing to infinity. But we do know that you can use this as a way to represent a large class of signals or a large class of functions even. So we also looked at how A and the coefficients that we have here, C and A, are complex, and we even discussed how this is the entire basis for solving differential equations according to what Euler was able to show. So if you recall, we talked about how the method of undetermined coefficients really stems from the fact that we are making a guess as to what the coefficient C and the coefficient lambda should be that can balance this differential equation. Now, of course, since because of this unique property of exponential signals, wherein their derivatives are just scaled by the coefficient. So let's say the first derivative of y of t would be lambda multiplied by y of t itself. And then the second derivative would just be the square, or the square of the coefficient lambda multiplied by the original y of t. So that gives us this really nice generalized way of looking for the solution to your function. Now, what this basically says is that if you plug this function into this equation, then you can find what the solution is. And it's kind of strange if you think about it, if you don't realize what this implies. So the implication for this, of course, is that it can be used for any number of different kinds of systems. And it is kind of strange if you think about it, that a single representation of a function can have so many different possible representations, or it represents so many different kinds of signals. So we did also show that what would happen when we would take C and A, which are both real, right? So we showed that if they're both real, then you would either get a growing exponential, a decaying exponential, or a constant, depending on the value of A. So once again, this shows us that, I guess in this case, for the first order differential equation, in most cases, A would just be a real number, or for any case of a first order differential equation, just because of the multiplicity and just because it's not a quadratic equation, which may have an imaginary part. So it's always going to be real, right? You're not going to have a first order differential equation in this form, at least, and then have some kind of sine and cosine for the representation of its solution. It's always going to be a real representation. So that's why first order differential equations or first order systems like resistor capacitor networks or some other types of systems always represent this kind of either, well, for the reasons of stability that we will probably go into later on. We can always show that the energy of a system is always going to decay towards zero. So the likelihood of an actual system having a growing exponential in its representation is very unlikely. Although they do exist in nature, there's always a limiting factor to the amount of energy or to the amount of amplitude or the amount of velocity or any kind of physical quantity to grow exponentially. But of course, growing exponentially does not necessarily mean that they don't exist. Nuclear fission is one of those things that have a growing exponential behavior. So that just really shows you that growing exponentials do exist, but growing exponentials also mean instability. And in the case of of nuclear fission, well, you have an explosion, right? So once it gets to a critical range, it continuously expands, or the reaction just continues until you have so much energy and then you have an explosion. So, of course, there's also the other possibility wherein the energy in the system is conserved and then there is no change. Of course, that's also a possibility, although also a rarity in a lot of situations. But it just also once again shows us that CE to the AT, even when it's real, does have some physical representation and does have some implications on the kinds of systems that you can solve based on the assumption that the solution is going to be CE to the AT. Of course, this isn't as interesting as, say, for example, if we had a purely imaginary situation. So if you have a purely imaginary representation for C, E, A of T, or I guess in this case, when A is purely imaginary at least, and C is still just real, and then we can then use Euler's representation or Euler's equation, which is given over here. So let me use the mouse highlighter. So, of course, what this gives us is a representation for a signal that has both an imaginary portion as well as a real portion. Now, you might be tempted to think that, well, what is this representing, right? So, notice that there are two coefficients here, right? And this real part right here is actually, you can have an example of a system that will exhibit this kind of behavior, at least for when you consider that the solution is going to be CE to the AD. There are situations, let's say, for example, if you had um, a capacitor and an inductor, right? So, sorry, inductor. So if you had a resistor and if you did not have a resistor at that, and you had some initial voltage VC over here, and you were supposed to measure the output at this point right here, the differential equation for this would actually can actually be solved to be something that would look like this. And if you solve for that using the initial condition, then the initial voltage VC is going to be the coefficient that you have here, and sorry, the coefficient that you have here, and this is going to be just zero. You can show that, you can try to solve this differential equation. And what you would then have is a continuously oscillating system wherein the initial voltage across the capacitor is going to be the initial voltage, and that's the amplitude of your cosine signal. So, of course, that's an example of an oscillatory system or an oscillator, since it keeps on going back and forth. So there are systems that do exhibit this type of behavior. Although this is sort of an ideal situation if you're using passive components. Of course, you can create oscillators using active components like transistors or operational amplifiers, because the truth is that most systems have some kind of resistance in them. So your capacitor is going to have some internal resistance. Your inductor isn't a purely zero uh, uh, coil. The coil itself is made out of copper or any kind of wire, so that means that there is some resistance to there. So what happens essentially is that the idealized version is going to have a continuous oscillation with respect to time, and it never dies down. Conservation of energy shows that that should be the case if you do not have any resistance. But of course, if you have any kind of resistance, then that means that you will be dissipating energy. Resistors usually transform voltage or electrical energy into heat. So that heat loss is going to cause the voltage amplitude of your oscillator to decay to zero eventually. So of course, these types of systems do not really exhibit this in practical situations because of resistances. But in the ideal case, as long as you have a capacitor and a resistor, you're going to have an oscillator, basically. So it's just going to keep on oscillating. Now, once again, that means that therefore, because CE to the AT does also contain that possibility for the solution, then once again, you can solve that because of the fact that CE to the AT can have this type of behavior. You might be curious as to, of course, in this situation, you can have a real, we can only have a real portion. The imaginary portion is usually regarded as zero, or the coefficient is going to be zero in most situations. And that's largely because our system here cannot display any imaginary numbers. Voltage cannot have an imaginary number. So it's kind of difficult to explain how in certain situations you can have a purely imaginary component. But of course, this does not mean that they do not exist. Once you go into electromagnetic waves or things like light or the propagation of radio frequencies or radiation, then the fact that you have an imaginary portion and a real portion also accommodates the fact that you can have those types of waves in electromagnetic waves. So the electrical part is usually represented as the real part of the signal, and then the magnetic part, which is usually 90 degrees out of phase or orthogonal to the electrical part, is going to be on the imaginary axis. So they are transverse, they are waves that exist in tandem to each other, but they do not directly interact. Of course, they do interact because of their interaction to resistors, capacitors, or any kind of system, really. But they themselves are on a orthogonal relationship. So if you're asking if there are situations where you can actually have real and imaginary parts in your signals, and the answer is yes, definitely there are situations, especially in electromagnetic signals. So I don't think that our curriculum right now goes into electromagnetism, or electromagnetics. But in electromagnetics, this is a very common representation where you would have a real part and an imaginary part as well. Not in the sense that you have phase and amplitude relationship as you would have in phasors, but what I mean is that the actual signal that it actually represents has a imaginary and a um, real part. Now we can also generalize these complex CNA to be complex numbers, in which case you would have this representation. And of course, we were able to write this down this way. So what you would then have is this representation where you have the real component, there would be an exponential part, and then this part, which would become a decaying or a growing exponential, is going to be multiplied by a signal that has both real and imaginary parts as well as some kind of phase, right? So the phase that we're talking about here is theta. Theta is defined by this equation right here. So what you would get is just the same oscillating signal. It would oscillate back and forth. But of course, that is now multiplied by a exponential, a real exponential, which means that the sinusoid, which could be the real part or the imaginary part, is either going to decay as we have seen here, or it's also going to grow exponentially. And what that means is that the amplitude is just going to keep on getting bigger and bigger while it swings until it reaches a point where it would be too large. So too large to represent physically, at least. But of course, in theory, you would be able to go to infinity. But before you get to infinity, most practical systems would already either explode or burn up, right? Or maybe it would have some kind of physical limitation. Um, so um, this generalized representation um, of CNA really does point towards the fact that CE to the AT is a shall we say, the representation that CE to the AT has or it contains is very wide and very vast. And once again, because of the fact that we can use CE to the AT, almost says that you can use almost any signal, an exponent, a decaying exponential, a constant, a growing exponential, a combination of a sine and cosine that has imaginary and real parts, a multiplication of an exponential as well as a sinusoid, and they're all encoded into this signal right here. But what is really important is that um, which signal is the solution is determined by the system itself. You can actually see that right here. Because remember, lambda and c are both unknown. They're coefficients that we do not know. But the question is, what determines the coefficients? And the answer is the parameter in your system, right? So the parameter isolates which kind of signal you would use as a solution. And I have no other way of explaining that except that this is a kind of bootstrapping situation wherein you're saying, let's use this generalized function, and then let's use our system to pick out which which kind of function that lives inside the generalized function is the correct solution. So once again, if Euler, or I guess if Euler did discover this, somebody would have discovered it. But just the fact that we can do this allows us to very easily understand our systems that we have. So We also do know, once again, if you know lambda, then you know the kind of system that you would have, right? So in control systems, we talk about how if the roots of the polynomial, of the characteristic polynomial, are real and distinct, then you would have all real components, and they would all be e to the at and e to the bt, where they would all be real coefficients. But of course, that depends on, once again, the roots of the polynomial that you have at this point right here. If the roots have real or a complex conjugate representation on them, then the solution is also going to be a complex conjugate, which means that it's going to have a real part, which means a decaying exponential, most likely. So it's going to be a negative value. The real number is going to be negative. And then there's going to be a oscillation part, and that oscillation part is going to be it determines the frequency of oscillation. So can you imagine that? How fast it decays and how fast it oscillates is all determined by the coefficients that live inside your differential equation. So once again, this really points towards the strength that exponential signals have when we talk about systems, or the way that systems behave. Once you get into the later chapters of control systems, I think that's going to be unit 4, or maybe you change the units, but once you get to time response, in time response, what you will find out is that systems are characterized depending on the definition of the system itself. So the system can either be underdamped, it's down, critically damped, it's overdamped, it's undamped. And that's all determined really by the coefficients, or by the roots of the polynomial. And you'll understand what I mean when you get there. But once again, this part about the exponentials is really what gives us the tools that allow us to understand how systems behave. And mind you, this is just a signal. It's just a generalized signal, but generalized so powerfully that it allows us to analyze a wide range of different kinds of systems. So if there are continuous time representations for exponential signals, this almost preludes that there must also be discrete time exponential signals. And you're absolutely correct if you think that. Um, but the way that there is some clear difference between the discrete time exponential signals and their continuous time counterparts. The similarities would have to start with, well, the fact that it has to be an exponential, right? Something has to be brought to the power of something. Now, if we write down our exponential, discrete time exponential signal this way, it's not very clear how it's related to the continuous time representation. So another way of writing this down, and for me, the clearer way of writing this down, but of course we will use this in a while, but we should be able to write down that this is also equivalent to saying something like C times E, which is the same number, and then we bring this to the power of beta times n. But this is where it sort of gets um, not confusing, but because of the fact that we can write down, and remember that n here is an integer, right? Unlike in the continuous time case, n is an integer, so I can rewrite this so that it becomes c e beta to the power of n, right? So c e to the power of beta multiplied by itself, basically, right? Because that's what you're doing by multiplying this by n. So this therefore means that if we were to write down that alpha is equal to e to the beta, then you just go back to this one right here. But it does have some strange representations, just because of the fact that now e to the beta, uh, we're sort of introducing this new base exponent or base number. Instead of using e to the beta, or instead of using e, we're using alpha, which is e to the beta. And we can write it, once again, we can write it down this way because of the fact that n is just an integer, right? Um, so this should still have the same implications. Let's say c is still going to be a complex number, and alpha can have many different possible values as well. And we can try to look into the effects of having this this number alpha, which no longer means 2.17 something, but it's now just any number, any real number. Alpha can be any real number at this point. So um, let's try to see what happens when we have different values for alpha. So let's start with the trivial case wherein alpha is equal to 0. So what do you think is going to happen if alpha is going to be equal to 0? Well, when alpha is going to be equal to 0, it's almost very clear that x of n is going to be equal to
0.
anyone?
0, sir.
Of course, it's going to be just 0. So x of n is always going to be 0 if alpha is 0, right? So that's why we call it the trivial case. Now, let's sort of isolate this, and then let's think of dividing this into subcategories, right? So now we have alpha is equal to 0, and then alpha is if alpha is equal to 0. So now let's look at the case where alpha is non-zero. So if alpha is non-zero, then there's going to be two branches that come out, right? There's going to be a branch wherein alpha is
Positive.
greater than 0. And then there's also going to be a branch wherein alpha is less than 0, right? Okay, so we know what happens when alpha is 0. When alpha is equal to 0, it's just going to be 0, right? Now let's sort of look at the first case when alpha is greater than 0. Let's look at this case right here. So the first thing that we should notice, or the other trivial case when alpha is equal to, when alpha is greater than 0, is when alpha is equal to 1, right? So when alpha is equal to 1, then what happens to x of n? When alpha is equal to 1, x of n is just equal to c. So it's sort of similar to the case that we had in the continuous time case, where it's always just going to be c, right? So regardless of the value of n, of course, 1 raised to the power of n is always going to be 1, so therefore x of n is going to be c. So it's going to be a constant all throughout. Now, what about when alpha is greater than 0, right? So we did say that alpha is greater than 0, but what happens when alpha is less than 1? Now we need to separate this, and this will become clear in a while why this happens, right? So when alpha is between 0 and 1, that means that the number here is going to be less than 1, right?
Yes.
So if the number there is going to be less than 1, then what that means is that we can create a sort of a representation where this is going to be c, right? At n is equal to 0, the value is going to be c. But when alpha is between 0 and 1, so it's not 0, it's not 1, but it's somewhere in between, then we can expect that the value at n is equal to 1 is going to be less than c, right? Because alpha is less than 1. And if alpha is less than 1, then c multiplied by alpha is going to be less than c. So we can predict that the value here is going to be less than 1, less than c, right? So that's going to be c times alpha, right? Now, what we will then begin to notice is that when we have alpha, or when n is equal to 2, we need to now take c times alpha and then multiply that by a number that is less than 1. So the next number is also going to be less than c times alpha, right? And this is now going to be c times alpha to the power 2. And then this is going to continue c to the alpha 3, and then that's going to continue to get smaller and smaller with respect to time. Now, this might be a little bit easier if we were to assign some value onto alpha, right? So let's say, for example, alpha is 0.9, right? So that's like saying if c is this value here, then c times alpha is going to be 90% of c, right? So 90% of c is not c, it's going to be less than c. And now we're saying, let's take c times alpha and let's multiply that by 90%, and then let's use that here. So that's even going to be smaller, but it's going to be smaller by an exponential amount, right? And then that's going to continue. So it's going to get smaller and smaller, and then it's going to approach 0, but it's never really going to get to 0. And the same case where you have what you would call a decaying exponential. So we have the same the same situation that you would have when it's what do you call this? When this is going to be it's going to be the same as you would have in the continuous time case. But there is a little bit of a difference here, that in the continuous time case, you get that decaying exponential when the coefficient is negative, right? So when a is less than 0, you get this decaying exponential. But that's not the case that you have here. Notice that the coefficient that we're using, since that's our base exponent, it's going to be alpha, right? And alpha gives you this decaying exponential when its value is between 0 and 1. And it's that situation because we are not looking at beta, right? We are not looking at the coefficient before the independent variable. We're saying what is the value of e to that particular coefficient, right? So this should have been our a, but in the case of the discrete time case, so again, you can combine this. So giving you this representation that we have right here. Of course, this is a generalized form. But now let's ask the question, what happens when alpha is greater than 1? Right? So, by the way, before I continue with alpha is greater than 1, if we go in the opposite direction, then that means that this is going to be also expanding towards the negative side. So whatever that is, that's going to give you, let's say, for example, c over alpha, right? So we are going to say c over alpha because that's going to be alpha to the negative 1. So a number divided by a number less than 1 is going to yield a larger value, right? So c divided by 0.9 is going to be a higher value compared to c. So that's going to expand as well as we go to the negative side. But if we were to instead look at what happens when alpha is greater than 1, then of course we can also write this down. Say that's n. This is going to be C over here. Now, when alpha is going to be greater than 1, then that means that whatever that value is, when n is equal to 1, the value at that point is going to be greater than C, right? And then the next one is going to be that amount greater than C alpha. So that means C alpha squared. And then that's the next one. It's going to be much greater still. That's C alpha cubed, and so on and so forth. And of course, if the value for alpha is greater than 1, then that means that it's going to be decaying as you go to the negative side. So this is a decaying exponential in the discrete time case. And then this is going to be a growing exponential. Right, so this is what we are going to be looking at. Now, yeah, so we've now looked at what's going to happen to the signal if we have an alpha that is between 0 and 1 and greater than 1. So when alpha is basically greater than 0. And now what happens when alpha is less than 0, right? So this is a little bit different. And we can start with just a simple case when alpha is equal to -1, right? So when alpha is equal to -1, then you get this representation. It's going to be very easy. That's C, and then that's going to be quantity of -1 raised to the power of n, right? But if we were to plot this, what would the signal look like? Right? So when because of this being a negative number, in particular the number is -1, then when n is equal to 0, the value here is going to be C, right? But then when n is going to be equal to 1, it's going to flip to the other side, and then that's going to be -C. And then if I go to the positive side again, that's going to be, once again, that's positive, and then it's going to go back to negative again, and then positive, and so on and so forth, right? So you have this flipping effect. It flips from positive to negative back and forth because of the fact that alpha is a negative number. Of course, once you bring a negative number to the integer or raise it to an integer value, then depending on whether or not the integer is even or odd, you can either get a positive or a negative value. So yeah, that's very straightforward, I think. But once again, the amplitudes are more or less the same. I mean, you get the same constant C over here, except that now it's going to flip back and forth between +1 and -1, depending on the value of n, right? So now let's try to look at what would happen when alpha is between -1 and 0, right? So that means that the magnitude of alpha is less than 1. That's what it basically means, right? The magnitude is less than 1, but the sign, however, is negative. So what do you think is going to happen? Since the number is negative, then we should expect that the same behavior we're seeing right here, wherein it goes back and forth between positive and negative, is still going to be there, except that now, depending on the value of alpha, since the value of alpha is negative, is less than 1, or the absolute value is less than 1, the magnitude is less than 1, and that means that for this, at least right here, it's going to be equal to C. But when you have 1, then it's going to be c or negative c and then alpha, right? So alpha, remember, is less than 1, so it's going to be less than c, but it's on the negative side. And then we flip back to the other side for the next one, so that's going to be c alpha and then squared and then c and then negative c, sorry, and then alpha cube and so on and so forth. So it's still going to have that sort of exponential decay to it, except that now the exponential decay also has this alternating behavior between the two signals. So this is sort of the situation where in the discrete time case you have this sort of special case, right? You don't have this kind of behavior in the continuous time, but it is a behavior that can be exhibited in the discrete time because now, once again, we are considering that the base of the exponent is a real number, but it does span the entire range of real numbers. So that means that it can go from negative infinity to positive infinity as well. Now, of course, there is going to be a situation just as we would have here, um, where and sorry, before I continue, of course, once again, you're going to have this part right here, wherein this is going to be negative c over alpha, right? So once again, if alpha is a small number, then it's going to decay as you go to the positive side, but it's going to expand as you go to the negative side. So let's now look at the case where alpha is less than negative 1, right? So we already have the case where it's equal to negative 1. So now let's look at the case wherein it's less than negative 1. So this one is also, once again, just pretty easy to predict. If the value here is going to be c, remember that alpha is going to be greater than c. So the value right here is going to be bigger in magnitude at least, but of course the negative sign is going to cause this to become negative c times alpha. And then the next one is going to be even bigger, but it's going to be on the positive side, and that's going to be c alpha squared. And then if you continue, it's going to go to a much larger number, c alpha cubed, and then negative. And then, of course, you would have that at 0, and then you would have a smaller number here. Since it is greater than 0, greater than 1, so the magnitude c divided by a number which is greater than 1 is going to be less than c, but it's going to be on the negative, and so what you have is a growing exponential. Okay, so I guess that the similarities between the continuous time and the discrete time is much easier to look at, or it's easier to see on the case where alpha is greater than 0. So you have that large similarity. But because we're now saying that alpha is any real number, you get this other side, this other representation for exponentials that grow and exponentials that decay, but while they're expanding or they're growing or they're decaying, they have this alternating function between positive and negative. So if we have this kind of behavior for alpha, we should also look at the effect that this has on general exponentials. So we can, I think, use the same representation, but if we were to look at it this way, it's not very clear how the sinusoids come out, because you can't see Euler's equation in this form. So what we usually do is we bring this back to the exponential form so that we write it down this way, right? So we can have e to the beta to the power n. And once again, I'm not going to write it down anymore, but we should be able to represent c instead of having a real and an imaginary part. We should be able to represent c as having a magnitude and an exponential part that has a real part. Oh, how did we write this? Okay. Real part and imaginary part. So this is going to have E, C, E. Sorry. Let's try to see how this is going to look like. So if I have a real part and an imaginary part, and then e to the j omega. Okay. So we have our real part right here and our imaginary part right there. Let's call this one phi. So this is going to have the real part is going to be equal to cosine phi. And then this part is going to be sine phi, right? So at least the exponential parts is going to have something that looks like this, or we can write down c is equal to c cosine phi plus j sine phi, in which case we can then write this down as, sorry, so there should be a c multiplying by that portion right there. So this right here is going to be the magnitude of that. So this entire thing should be multiplied by c and then magnitude. So this means that we have the magnitude of c multiplied by e and then j pi. Okay, so if we can write down the c part as having this polar representation, then we can then rewrite this as c e to the j phi times e, and then we should be able to break this down. Instead of being beta times n, because beta is also a complex number, so beta is going to have a real part multiplied by added with an imaginary part, which let's call this RCW and CW so that it's easier to keep track. But then this entire thing is going to be multiplied by n. So this means that this is c e to the j theta times, phi multiplied by r times n multiplied by e to the j omega and then n, in which case we can write this down as the magnitude of c multiplied by e to the power r times n, and then this part is going to be e j omega n plus j, not j, but this is just going to be phi, and then we can write this down as e to the j or n, e to the, and then we can write this down as cosine omega n plus phi plus j sine omega n plus phi. And then this would be your general exponential. Okay, so once again, this does allow us to create this vast representation of exponentials. Um, Once again, some of the exponentials are, this is going to continue being a real part. So, of course, r is just going to be a number, any real number. So this is either going to be decaying or expanding. And then this is going to give you some kind of oscillating representation or a sinusoidal representation here. So this is just your magnitude. And this also, once again, gives us the different possible representations for a sinusoidal signal. Now, we did skip one part regarding this, um, and I'd like to talk about this the situation wherein we might have these pure exponentials, pure imaginary numbers, right? So um, there is this strange behavior that sort of emerges because of the fact that you have a sine and a cosine right here. So the strange behavior that we have, and we're really isolating the part where we have discrete time uh, sinusoids because they do happen, especially when the real part right here is zero, right? Or when the real part, or when C is just a real part, and then uh, B beta right here is just an imaginary part, right? So if we were to isolate the situation where let's say we had our complex exponential c e to the beta of n, and then if we said that c is just a real number, in this case, let's say that c is equal to 1, and then let's say that beta is just a imaginary number given by j omega o, right? So some omega o that you would have right there. So this would then mean that this function right here would just reduce to this one, right? E to the j omega o of n. Now this does have some strange behavior that you just don't have in the continuous time case. What I mean by that is that if I have a, let's say, an exponential signal, right? So an exponential signal in terms of the continuous time. So if I have e to the j omega o of t, we know that this is really nothing more than something like that, right? Now, we can show that this is going to be periodic, right? We can show that this is periodic because we can always find a t, a tau that we can add to this so that we can test for periodicity. So this means that if we can show that e omega o times t plus, or sorry, let me rewrite this. If we can show that e to the j omega o times t is equal to e j omega o t plus tau, then that tau is going to be the period of this signal right here. And you can show that you can show this mathematically, that this does in fact exist, right? So we can show that by solving it right here. So if this is going to be something like cosine omega o of t plus j sine omega o of t, then the right-hand side, by extension, is supposed to be cosine omega o t, or wait, let me very quickly rewrite this as omega o plus omega o times t, omega o times tau, right? And then this is going to have some sine, and then omega o times t plus omega o times tau, right? So you can always write it this way, right? So this mere fact just basically means that the only way that this holds true is if the right-hand side is equal to the left-hand side, right? That's all that it means. But we can show that there exists a number tau that you can add to this that will make this true, will make this statement true. So, for example, this one right here, we can write this down as cosine omega o of t cosine omega o of tau minus sine omega o of
Speaking the
t
alien language.
sine omega o of tau. And then this portion right here,
Can you see I'm on
you can have your
so
plus
may-
j, and then this is going to be sine omega o of t cosine omega o of tau
Sa todo mo.
plus cosine omega o of t sine omega o of tau, right? So you can show that these should be true, right? Now, the question that we might ask ourselves is, what values, or when can the left-hand side of this be equal to this right-hand side, right? So there's really only several possibilities for that. The only way that this entire left-hand side becomes equal to the right-hand side is if this becomes 1. This entire term is going to be 0, right? This entire term is just going to be 0. So this cannot be 0 because this always exists for any value of d, or for most values of d. But this should always be 0. And in this case, this should still be 1, and then this should also be 0, right? So basically what this means is this can only be true when this is true, right? So
What?
only when cosine of omega o times tau is equal to 1, and when sine omega of tau is equal to 1, right? So this means, therefore, that this can only hold true if this equation were equal to 1. Now, the only way that this equation can be equal to 1 is if when can this be only equal to 1 for any value of tau right here, right? So we can also show that this is always this is always going to be equal to 1 if this were some cosine and then 2 pi times some let's say k, right? So if I have an integer k, um, then this is always going to be equal to 1, right? So when k is equal to 0, cosine 0 is 1. When k is equal to 1, cosine 2 pi is 1. When this is -1, it's still 1. When it's -2, it's still 1. It's always going to be 1, right? So that means that we should be able to assign this and that, right? So that we can then show that omega O times t is really going to be equal to 2 pi times k, right? And that therefore means that tau can be, or tau should be equal to 2 pi times k over omega O, right? So this means that tau can only, the only value that tau can be is going to be 2 pi times k omega O. Now remember that tau is supposedly the smallest real number that you can add to t that would make this equation true, right? So remember that for periodicity in the continuous time, you need to write down that you have this condition, right? So it has to be the smallest number. Now, the smallest number that you can represent from this is when k is equal to 1, right? So when k is equal to 1 would be the smallest number. So therefore, the period has to be, the proof of this would have to be that the period has to be equal to 2 pi over omega O. That's the only way that this equation can be shown to be periodic, right? So 2 pi is equal to 2 pi, tau has to be equal to 2 pi over omega O, and you can show that right here. Now this is important because this also means that the periodicity of the signal depends on omega O, depends on the frequency that you're applying on this quantity right here. And this also means that every value of omega O is going to generate a unique signal, right? So that means that um, when omega O is equal to 1, there is no other omega O, another value of omega O that will satisfy this equation, right? There is no other value. Every single value of omega O is always going to generate another frequency. There are no frequencies wherein they have different values, but they evaluate to the same signal. Does that make sense to you? This means, if I could write this down graphically, it means that if this is an omega O, some value of omega O, then another omega O is going to generate another signal. And these two are not the same, right? This tau is never going to be the same as the tau that you have for this other signal. Change omega O, you get a totally different signal. This is what it means. They're still periodic, it would still be periodic, but their frequencies would not be the same, so they are not the same signal, right? And you might be thinking, why am I talking about this? Of course they're going to be different, right? They have to be different. It has to be unique. Every single value of omega O is always going to create a unique signal. Who would be stupid enough to say that that's not true, right? That's obviously true. I mean, why are we going through all this proof? And the answer is because it's not the same in the discrete time case. So this isn't really important, this proof right here. I just wanted to show that that this signal is periodic and that every single value of omega O will always yield a unique value of tau, and so you always get a different signal for every single possible value of omega O, right? So every omega O is always going to generate a unique value. That's what we're trying to say. But this isn't the case in the discrete time case. And what we mean by this is that this is supposedly something that is periodic. And by the same logic or the same derivation that we went through, you can show that we can show that you can have some integer. It's possible to have an integer that you have here, and then that integer is going to be related to 2 pi over omega o, right? We can show that. But there is also this other strange thing that happens. And this is, it's based on the principle that if we were to add some value to omega o over here, so if we were to take our omega o and then let's add a omega onto omega o, right? So we're saying that this is our base frequency, but now let's say that we're adding some offset omega, right? This is another value. And we're saying that this is going to, if supposedly in the continuous time case, if you increase omega o, you get a unique signal. Something weird happens when you're in the continuous time case. And it's the fact that if you increase the value of omega so that the value of omega is equal to 2 pi, right? If it's equal to 2 pi, what happens to this signal right here? If omega is 2 pi, which means we have effectively increased omega o so that it's now equal to omega o plus 2 pi. This means that we should be able to write this down as e j omega o times n plus j 2 pi times n, right? And that's all going to be in quotations. So this means that we should then be able to write this down as e j omega o times n times e j 2 pi of n. Now this is where this gets a little bit strange, and this used to this confused me the very first time I saw this, because e j 2 pi n is equal to 1. And we can show that this is equal to 1 by using Euler's equation, because e j 2 pi n is going to be cosine 2 pi n plus j sine 2 pi n, right? Now, for any value of n, where n is an integer, this is always going to be equal to 1, right? And this is always going to be equal to 0. So cosine of 2 pi n is always 1, and sine of 2 pi n is always 0. So therefore, it's equal to 1. And so therefore, this is just equal to 1, right? So if we do this, then we are saying that e j omega o times n is in fact equal to e j omega o plus 2 pi multiplied by n, right? And in fact, this doesn't just end right here at 2 pi. For any value, even if I make this 2 pi times k, so even if I were to add this by some increment of 2 pi, this would still just be the same, because an integer multiplied by another integer is still just an integer, right? So 1 times 1 is still just going to be 1, so that's still going to be 2 pi, and that's still going to be 1. N let's say n is 3 and k is, let's say, 33, right? So that's, what is that? That's 99. So cosine 2 pi times 99 is still just going to be equal to 1. So this is always going to be equal to 1. So strangely enough, exponential signals or periodic sinusoids in particular, in the discrete time have a periodic nature such that e to the j omega o of n is equal to e to the j omega o plus 2 pi k times n, right? So if we were to use actual numbers, this would mean that e, j, and then let's say we have pi over 2 n, right? So let's just say we have that's our omega. We have pi over 2n, right? That would then mean that this is equal to e j pi over 2 plus 2 pi, right? And then n. And the weird thing about this is, of course, if we evaluate this, this is going to be equal to 5 over 2 pi, right? So it's this really, these two are not the same, right? You can clearly see that this is not equal to pi over 2 plus 2 pi. This is greater than this by a factor of by 2 pi. It's greater than this by 2 pi. But this signal is the same as this signal, right? And so this is this weird behavior that we have with complex exponentials. It's like saying that there is only a subset of numbers that you can use to represent frequencies in the discrete time case. And this is true. In the discrete time case, increasing the value of the frequency omega would continuously give you different signals. The frequencies would just get faster and faster. But what happens is that in the discrete time case, it doesn't matter if you increase your omega. Eventually, you're going to roll back to 2 pi. And once you get to 2 pi, you go back to the original signal that you had. Now, of course, this isn't some mathematical trick that we're doing. This is a side effect of the fact that our independent variable is an integer. And this is absolutely true. You can show that you can try to do this in the continuous time case and it would not give you the same result. And that's because t, the independent variable, is not an integer. It's a real number. And the real number would yield many different possibilities. There is no way that in the continuous time case, this would be true. This would never be true in the continuous time case because multiplying t with this part right here would not be the same as multiplying this by an integer. Because once again, an integer multiplied by another integer is just another integer. Whereas a real number multiplied by an integer would give you a real number. A real number multiplied by 2 pi would give you another number that is not equivalent to 1. You wouldn't be able to do this in the continuous time case. There would be some situations, there would be certain values of t wherein it would become true, especially when the value of the real value multiplied by the integer would yield an integer representation. So let's say if n were exactly 2, right? Not 2.1, not 2.2, not 2.3, then you would be able to do that. But it's not a general case. It would just be a special case. So it would be an exception, whereas in here, any value of n would always evaluate to 1 when you substitute e to the j 2 pi multiplied by some integer. So that's the main difference. And it's this sort of unintuitive nature of discrete time representations or discrete time signals. I I'd like to take some time to really show this behavior of um, um, the discrete time signals. So um, one moment. Hmm. Let me save this for a while. One moment. I'll try to bring up. Um, my computer is getting slower, so I'll try close some applications. Ah, hmm. Okay, so I'm having some technical difficulty.
Mana kasi dong? The sunset is sleeping. Kagami ko dito ni Boy. Boy, boy, eh? Hi. How to be you, Toy Toy? Tinahan yung kamo apil nila dong. Di ka mauwaw dong. Sila may entrance ng mga na dong.
Wala.
Pero wala man.
Libre lagi na sila.
Okay.
Ikaw, ganahan ka mo
Hmm.
mo.
Kung bakante. Ah!
Invite anak nila.
Ha?
Sige, invite anak nila.
Hindi ka mo invite ni Jamali.
So, kung sa katong invite?
Oo. Pinangga man ko.
Ha?
Pinangga man ko. Buotan man ko. Good.
I raised you well.
Basin.
What?
One moment.
Uno
I'll
momento.
try to see if I can restore some of control of my computer. Just one moment.
Online
Unsa dapat
Dapat ato. Unya, temporary permit pa jud wala mahuman ang permit ba? Atay yung kontraktor ana.
right.
Dawin sa mga klase. Lutas ba sa kuan eh? Davao.
Today I'm hosting a 30-person NBA 2K